telling you something about results in quantum complexity theory. And I'll start saying a few more things about the quantum K-set problem and a version of that which one would say avoids the sign problem. Yeah? So we have a specific word for this actually, but so I mentioned before. Okay, so I mentioned before there is the classical satisfiability problem, which is known to be in NP and is NP complete. So that's kind of the caricature of a classical optimization problem. Then there is the quantum satisfiability problem, which I argued is QMA complete. So that's kind of the generic kind of quantum optimization problem. And then there's something that is in between. And I say a few things about the results that we've proved about that problem. And then I'll switch over to results that of hardness results that relate to models that are geometrically local. And in my notes, I had prepared an explicit, basically proof how I showed in the last lecture, I showed how to map a circuit onto a Hamiltonian. Yeah, but then that Hamiltonian, I said you could massage it into being 5 local, meaning a sum of 5 body terms. But in my notes I had prepared a procedure in which I take a quantum circuit and I map it onto, again, a 5 local Hamiltonian, but this Hamiltonian is defined on a 2-dimensional lattice. Yeah, but I think I won't have time to actually explain this in detail, but if you're interested you can look at it in the notes. Okay, so let's just say a few more things about this quantum K-set problem and as the sign avoiding version of this. Okay, so what was quantum K-set? So we had a bunch of projectors, say M of them. So they're projectors. And we had some number B, which is the 1 over some polynomial. And each of these projectors acts on k qubits at a time. That's sort of a k-body operator. And we have to decide whether there exists a state such that for all projectors, that state is annihilated by the projectors, or for all states, the smallest eigenvalue of this operator is at least b. It is bounded away from 0 by some amount that's 1 over polynomial. I could look at this in terms of a Hamiltonian also. I could say, well, I could define this Hamiltonian, the sum of projectors. And then this question is saying, is the ground state, so okay, this Hamiltonian is the sum of projectors, so the lowest eigenvalue is possibly 0. And I said in the previous lecture, if this lowest eigenvalue is 0, then every one of them, of course, has to have eigenvalue 0, so this has to be true. So we ask basically whether there is a ground state of this Hamiltonian that is the lowest eigenstate of every term individually. Or this is not the case. If this Hamiltonian satisfies this constraint, we call, and this is made, I know this has been confusion, there's led to some confusion in, I think, among people who are more familiar with condensed matter language. We call this Hamiltonian frustration free, if this is true. It doesn't mean, okay, so why do we call it frustration free? Well, it exactly captures, so if you have look at what do we call frustration in classical spin systems? So generic example of a frustrated classical system would be something, I have 3 spins, and they're coupled by an antiferromagnetic interaction. I can never simultaneously satisfy this constraint, meaning that the spins are misaligned, this constraint and that constraint. Okay? So this question is kind of asking the question, is there a way of satisfying every constraint captured by these projectors? And if that's true, we call this Hamiltonian frustration-free. Because it's not this kind of Hamiltonian, it's we're talking about the quantum generalization of this. It's not of this form. This model has frustration. Whereas if I find such a state, I say there's no frustration in the ground state because I can satisfy every constraint simultaneously. In the notes, I give you another example that you may be more familiar with, which is the quantum dimer model at the Rockshot-Pevelson point, where the Hamiltonian is a sum of projectors, and the ground state is a zero eigenvalue state of every one of those projectors individually. So you can verify that yourself. Okay, so now...
Good question. Is
Yeah?
this property somehow, is it, if I have a Hamiltonian but I don't tell you how I split it up into projectors, can one uniquely decide whether this property holds or not?
Yeah, of course it is... yeah, of course, if you have a Hamiltonian, this decomposition of projectors is not unique. Because you could say, I want to have like one local projector, maybe you have to split it up differently. So it's cleaner to ask it in terms of projectors. But you can also say, well, if there is a way, if I take the Hamiltonian, if there is a way of defining local projectors on few qubits at a time, and the ground state satisfies all these constraints, I should call this frustration-free.
And is it quick to check if I hand you a Hamiltonian whether it has that property, whether there exists such a decomposition?
No, but whether it's frustration-free?
Yeah, whether...
No, this is actually this question, because, so this quantum K set, now in this case I'm already given the projectors, but this quantum K set problem is in general QMA complete, right? And I'll show you at the end of this lecture that if K is 2, it's easy. And I'll show you how to do that. Now, you say, okay, what about these projectors? Now, of course, we're not hung up about projectors, right? We can have any Hamiltonian, which we write as a sum of terms here. We could add the identity to it, doesn't matter. It doesn't change the property of the spectrum or the ground state. And we could say, well, I could look for every term here, I could look at its ground space. Yeah? Define the projector onto its ground space. So that gives me a bunch of projectors. Those ground spaces. So then I can ask, that's equivalent to this question, is there a state that lies in a sort of intersection of all these ground spaces? Right? So that's really asking, if I look at an individual term in its Hamiltonian, I could minimize its energy and find the state that minimizes energy. I can do that for another term. But we're asking here whether there's a state that is the minimum energy state of all these terms simultaneously. This is generally not true. That is because their systems are frustrated. They have competing constraints that all want to be satisfied simultaneously. Okay, so what about variants of this problem? Okay, so I mentioned so we can look at the classical SAT problem. It's a special case. Now, let's look at another case. So what I said about the classical SAT problem is that in that case the projectors were something like this. Zeros on the off diagonal and stuff on the diagonal in the standard basis, in the qubit basis or the spin basis. And of course, if you find a ground state that satisfies all the constraint or a satisfying assignment, that state will be something like, well, I think I had an x1, xn. It will just be a product of bits, right? Now for quantum set, the projectors are general, arbitrary here, right? There just needs to be a projector. And the ground state, if it's true, the ground state is just some general n-qubit state, right? These are in principle 2 to the n, right? There's n qubits, so I have 2 to the n possible states, so there are 2 to the n of these coefficients. So now the intermediate case is the following. Let me just write it up here. So what about if the projectors are of the following form? Well, first of all, they're real. That's the first constraint. And secondly, well, I don't care about this on the diagonal, but on the off diagonal, they're strictly less than 0 or 0.
What do you mean by real for the whole matrix? Each element is real?
Yeah, all the matrix, yes. But in this standard basis, if I write down that matrix, which is some small matrix, you know, like on an 8-dimensional space, let's say it's 3 qubits, then all the entries in this matrix are real. So what's special about this? Well, you've seen probably, so if I write down something like this, you notice that if I would look at an object like this, I take the standard base and I look at an off-diagonal object, this has to be less than 0, right? It's a sum over these terms. And this is what you call, or sign avoiding, or no, let's see, Hamiltonians, let me see, I should erase this, Hamiltonians without a sign problem. This is a Hamiltonian, H has no sign problem. Now, when we started studying this in the context of complexity theory, we were surprised that for such large class of Hamiltonians that have no sign problem, there was no single name. You always say it has a sign problem. We can do quantum Monte Carlo. So we called these, and maybe you won't like this, we called these stochastic Hamiltonians. And the idea is that they're kind of in between stochastic, meaning, you know, classical, and Markov chains and so on, and quantum. And what's so special about these Hamiltonians? And you can easily prove this. So if you have a condition like this, well, we can define this matrix. We take delta to be very small, such that if you look at this matrix, on the on-diagonal terms of this matrix are positive, right? I have the identity minus something that's small, so that can be made positive. And these guys, well, this was negative, so therefore, this is also positive. So the matrix G, as a matrix in this standard basis, is a non-negative matrix. Yeah, and of course it's also clear that the ground state for H is the state with largest eigenvalue for G, right? Because I take minus. We know it's a very standard result that was known about non-negative matrices, namely that if I look, so let's say if I look at the largest eigenstate of a non-negative matrix, that state can be written as something like this, where these are non-negative. No? So the point here is that this state, this largest eigenvalue G, is the ground state of H. And what this is called the parameter radius theorem. It's a very simple, very standard result in matrix theory. That that state has coefficient. These alpha coefficients are non-negative. If for a general quantum state, these coefficients are complex, or more restrictively, they can be positive or negative. So these non-negative coefficients, if I look, I could take them squared, and I can look at them as a probability distribution. So a Hamiltonian that's constructed in this way, or in general something that has this probability as Hamiltonian that's real and has non-negative off-diagonal elements, has a ground state which you would say is nodeless. Well, there could be nodes where this goes to 0, but otherwise all the amplitudes are non-negative. And that's why you can do quantum Monte Carlo on these systems. And that's why there are, simpler, more classical algorithms to find this ground state. Right? So you'd expect that for Hamiltonians or for projectors, for which this is true, finding the ground state would not be QMA complete. And indeed, we can prove this. We can prove that, let's see, okay, so we have a version which we call stochastic K-set. It's like that problem, except that you have an additional constraint on these projectors having this property and being real and having this property. Stochastic K-set is, well, now I'm going to confuse you because you don't know what MA is. It's MA complete. Well, MA is a probabilistic version of NP, and everybody believes that MA is NP. So let's just make it simple. We're going to show that stochastic K-set, which would be sort of asking this question for Hamiltonians that avoid the sign problem, that is not QMA complete. We believe it's not QMA complete, but it's more classical. It's NP complete. Do you have any questions about this? This is just because I want to make contact with what you've heard about what we can do for Hamiltonians that don't have a sign problem. And of course, these are ubiquitous, right? We have many Hamiltonians, Heisenberg models, and most models with bosons. I can give you a whole list of models for which you can just check whether this is true. Right? You can just write the Hamiltonian and check this, it's okay. And that's probably what is done also in practice. Okay, so if there are no more questions, I'm going to talk about geometrically local models. And for that, if you're following with the notes, I'm actually going to skip to page 8 in my notes, because I'll do page 5 and so on a little later. Okay. So I think one of the things I like to say about the stochastic is that it also shows that, I said we believe QMA to be different from NP. And where does that difference lie? Well, it lies in these fermionic models that have a sign problem. It really lies in, I think intuitively, it relates to the question that, quantum Monte Carlo doesn't always, for many models, doesn't work. You do have a genuine sign problem that you can't get around. Okay, so I promised that I would talk about models on a 1D and 2D lattice. Now, instead of showing that, how you prove that some of these models, finding the ground state energy is also hard, I just want to throw the result at you. Which is, I think, quite surprising. It was a big surprise. So this was shown by Aronov. This is not Jakir Aronov, this is Nice. And Gottesman. It was shown that stated one-dimensional, referring to one-dimensional chain, 12-state local Hamiltonian problem is QMA complete. Okay, so this is code language. Okay, so the idea is that one-dimensional chain, they constructed it's not constructively, I mean, if it's this construction where you take this quantum verifier circuit of any QMA problem and you massage it into a Hamiltonian, and that Hamiltonian is a Hamiltonian of a one-dimensional chain, and there are not qubits here, but there are 12-dimensional particles here. And the Hamiltonians is just, some nearest neighbor interaction between these 12-dimensional particles, not translation invariant. And so, what it says is that it's hard to determine, the ground state energy with 1/Pauli accuracy. Okay, so why is this surprising? I didn't think this was going to be true. Well, we all know that one-dimensional systems are easy, right? One-dimensional systems are a lot easier than two-dimensional systems. As we heard this over and over again in lectures. For one dimensions, we have DMRG, which works very, very well. Whereas for two dimensions, we don't have a good handle on how to do the optimization over, of variational states like the PEPs. So why is this surprising? Why do we think that one-dimensional systems are easy also? Is that classical one-dimensional systems are easy. This problem, classically, is in P. I'll give you later an efficient algorithm how to find the ground state energy for any classical spin change. Whether it's very practical is a different question, but it's an algorithm that scales linearly with the length of the chain. Well, it scales badly with this dimension, the dimension of the sort of the spin here, but if that's small, it's a fairly good algorithm. So classical one-dimensional systems are easy, so you'd expect that quantum one-dimensional systems are also easy. So it also suggests that, okay, so Frank was talking about matrix product states, right? And matrix product states are characterized by a bond dimension. This is the dimension of the matrices in the matrix product state. So it's like, this is alpha, beta, or something. So in most numerical optimizations, you take this dimension to be constant. But you could say, well, I could of course also look at models where this scales, this increases if I take a larger chain and let this grow also. That still gives you an efficient algorithm, right? Because the DMRG procedure is polynomial in this bond dimension. But let's assume that matrix product state with growing bond dimension were a good ansatz for this ground state problem. Well, then this problem would be an NP, right? Somebody could give you the matrix product states that solve the optimization, that are optimal to get the energy eigenvalue, to get the ground state energy. Giving these matrices is a classical proof, right? If you're giving these matrices in the matrix product state, with that in your hand, you can efficiently estimate the energy. But we know that there are hard problems that are even QMA complete. So it says that there are models for which even a matrix product state with bond dimension growing as a function of n are not good ansatzes to the ground state to the ground state.
So how do I reconcile this with the sort of proofs that we had earlier that matrix product states were good ground states? But what part of that? What assumption of that proof is being violated in this case?
Yeah, well, so there's there's a gap between the rigorous results and the hunches and intuitive beliefs. That's one thing. But so there's one rigorous result, which Matt presented, I think, and he said if the Hamiltonian has a gap, so I have a class of Hamiltonians, And there's the ground state here, the ground state, the E0 here. And between E0 and E1, there is a gap for these models, and this gap doesn't diminish with growing system size. Yeah? So for models which have, for which you have promised a gap, you can prove that, you know, there's a decay of correlations, and that Hastings proof explicitly that a matrix product state with bond dimension growing like this is a very good approximation to the ground state. Yeah, so for those models with a gap, you know that your problem is in NP. And maybe it's even easier than that, we don't really know. But if you don't have a gap, well, you know, at critical point, you still believe that, well, I mean, generically it's hard, so
So the point is enough of these Hamiltonians have no gap.
yeah, they cannot have a gap, right? And you know, there's nothing that could even have an exponentially small gap. So, okay. Now, let's now kind of play devil's advocate a little bit and talk about accuracy. Because there is definitely a gap between our heuristic methods that work well and a result like this. So where is the gap? Well, a big thing is that in this reverse result, we talk about a lot of accuracy that I mentioned. Right? We really want to estimate the ground state energy with high accuracy, so you can believe that finding that particular ground state is hard. Yeah? So other low-lying states would not be good. If you find those, they would not be good. Now, so you could say, well, this is too strong. Yeah, so for example, so I have here like a little discussion, a physicist would say, lab to H, the lowest eigenvalue typically scales with n. It scales like some mu n. Yeah? So why don't we just say, well, we want to estimate this number. We basically want to estimate u, right? The scaling of the energy. And this is estimating the energy density, right? So estimate u with some accuracy epsilon. How hard is that? Well, then I say, well, then you shouldn't talk to me because there's always an efficient algorithm that does this. So it's not interesting. It doesn't capture any of the properties of my Hamiltonian. Whether it's in a 2D lattice or a 1D lattice or a 3D lattice. Now, the algorithm that I'm going to give you is not maybe the one that you want to do in practice. Because it is an algorithm that runs in polynomial time, but it doesn't always mean that it's a nice algorithm to, you know, it's a practical algorithm. Okay, so I call this the Homer-Simpson way of estimating ground state energy, or the ground state energy density. And so it's a very simple argument that goes like this. Let's say we have a 2D lattice, and we're going to divide the lattice up in blocks. And these are blocks L by L. This is L by L. And now what we're going to do is we have the Hamiltonian that coupled also qubits between this block and this block, where we're going to forget about those terms. Okay? So first we divide up the lattice in blocks, L by L blocks, and L is going to be parameter. Secondly, we omit terms in H which couple blocks. And then, for each block, which is just some constant size, some small size, we can do exact diagonalization. So, just do the simplest method possible, line shows or whatever, on a block. Yeah? So, because now when we omit the interactions between the block, we just have the sum of this decoupled systems. Yeah? And the idea is that this block L is something that is of order 1. What I mean is that if I do this procedure for growing system size, I'm going to keep my L fixed. Okay, now I want to estimate what is the error that I make doing this. What is the error that I make doing this in estimating the ground state? Well, I can bound, let me bound the difference in the Hamiltonians, and that let me will bound the difference in the error that I make in the energy. Okay, so I've replaced my Hamiltonian by a Hamiltonian, which is the sum over disconnected blocks. Okay, so how does this scale? Well, how many blocks are there? They're ordered n, total number of qubits, divided by L squared blocks. Right? And each block, how many terms do I lose? Right? How many terms do I forget? Well, that scales like the perimeter of the block. Right? So that scales with L. So this error, or this thing, is order n over L. The fact that the number of blocks scales with the volume, or one of the volumes blocks, and the number of terms I forget scales with the perimeter is the trick here. Right? So the difference between these Hamiltonians, that it goes down when L grows. So now I can say, if I bound this, then you can also show, let's see if I can do this here. Let's see, this is the lowest eigenvalue, this is its density. And now, of course, I want to compare that with the lowest eigenvalue that I get from this. Yeah? So what do I do to get this? I take every block, I do exact diagonalization, find each blocks, and I add them all up. Yeah? So this can be bounded as 1 over n, the norm of this block thing. So this is bounded of 1 over L. So if I want to estimate the energy density, I can do that by looking at these blocks, and I get an error of 1 over L. And I can call that 1 over L, I can call that epsilon. So I have estimated the energy density up to an error epsilon by doing this block procedure. Okay, so what kind of effort do I have to do? Well, I have to do like n over L squared of these exact diagonalizations. Let's say it's n exact diagonalizations. And of course, this exact diagonalization is something where I have to diagonalize it to the L to the squared matrix. But this is an effort that only scales with L. It doesn't scale with n. Right? So that's why this is an algorithm that is efficient in n, but it's not very efficient in accuracy. And if I take the accuracy to be a small constant, let's say a third or 10th, that gives me an algorithm that scales, linearly with n, and just has a big prefactor, which is the cost of this exact diagonalization. So this shows that for any geometrically local system, I can always estimate, I have an algorithm to estimate the energy density in this way. Now, I'm not advocating that this is the way to do this, because if L gets large, this is not very nice. But it shows that I cannot prove anything hard about this problem, right? Because it's not hard, according to my, sort of my standards. Okay.
There's some assumption about these couplings being bounded.
Yes, yeah, of course you have to, but I think that's typically the case. You have to, I threw it away that you have to say, okay, there's some the coupling strength J that comes up here, then of course. Yeah, but that's typically, it's not, if you have a Hamiltonian, well, okay, if it's not true, then you could use perturbation theory or other methods. Otherwise, you assume that the couplings are of equal strength and they're constant, they're not growing with system size. Okay. Any questions about this? Okay. So geometrically local Hamiltonians, and I want to Okay, so that result is quite non-trivial, how this is proved. And prior to that result, I proved with a postdoc some other result, basically the same thing on a 2D lattice, so it's less strong. But I want to say something about how to change Hamiltonian. So, okay, so in the theory of NP and NP-complete problems, you know there are many, many NP-complete problems. So how do you show that these are all NP-complete? Well, as Ash was saying, we do that by doing reductions. You map one problem on another. You map SAT on an Ising spin or Ising spin model on SAT. How do we do reductions between quantum problems? Now, I have to say that we don't know this very well. This is one of the open questions. But there's one trick that we use, and that's perturbation theory. And it's actually kind of obvious that we will, that's a trick that we use, because this is also, to go from one Hamiltonian to another, you use this perturbation theory. And let me show you how you use perturbation theory in complexity theory. Okay, so prior to this, we showed that two-dimensional, so 2D lattice, two local, no Hamiltonian is hard, is QMA complete. And the way we actually showed this is we first proved this for 2-dimensional 5 local Hamiltonian, and that's the constructions that I have outlined in a note. So it's not actually too hard to modify Kitayev's proof to show that if you have a 2-dimensional lattice, 5-body Hamiltonian acting on this lattice, that there's a class of problems for which the ground state energy problem is hard. But the question is, how do you go, if you've shown that this problem is hard, how do you show that this problem is hard? And actually, maybe I want to say one thing about, before I show the use of perturbation theory. This story doesn't end here. And so, once you understand also the tricks that you do with perturbation theory, people have also shown that, because this is still general interaction, so you say, well, what about Heisenberg model? And so I think this is a result by Frank Verstraete and Norbert Schuch showing that finding the ground state energy with high accuracy for 2-dimensional Heisenberg model, antiferromagnetic Heisenberg model, with a random magnetic field. So you have a 2-dimensional lattice, to the antiferromagnetic Heisenberg model, and you have a field, a magnetic field that is locally varying. It's not, it's just, it's set to a certain value, and then you say, okay, do you calculate the ground state energy now for me for that particular configuration of the field? And there's more work on that. So there's a whole, you can keep on simplifying this problem and say, well, is this still hard? Is this still hard? And until maybe you find an easy problem. Okay, so what's the use of this perturbation theory? What's the role it plays? Okay, so in physics, we use perturbation theory following way. So we have a Hamiltonian, which is a large part plus the perturbation, characterized by perturbation times lambda. And we use perturbation theory to construct an effective Hamiltonian for the low energy sector of this perturbed model. For example, H is the Hubbard model, for U much larger than T, and then H effective could be like the Heisenberg model, right? And then you can go up to second order perturbation theory, you get the Heisenberg model. Higher orders give you, well, generally, I think for Matthew Fisher's lecture you heard, you could get 4-body operators. So what is important is that H effective can be typically many-body, meaning that it could couple, 2 spins or 4 spins at a time. And where H is few-body. So generically, and this is like what you're given with the physics, but H effective can be, a Hamiltonian that interacts many more qubits at a time. One model, okay, I won't give you an example now. So that gives an idea. If I now, so here in this problem, I have a 5-body Hamiltonian, which, is not the kind of Hamiltonian you would see starting from some, basic description of electrons or something. Or 5 spins coupling at the same time is pretty high. So how can I relate that to a few-body Hamiltonian, say 2-body? Well, I can run perturbation theory in reverse. So in complexity theory, we start with H effective. Say 5 local. We're given a family of 5 local Hamiltonians. It's not a concrete family, it's an abstract description. And then you can say, well, how can they arise from a few-body Hamiltonian? And we use what we call perturbation gadgets, which are just like running, like I said, running perturbation theory in reverse. So we have gadgets. Gadgets means like it's a little trick. Let's say, give me any 5-body Hamiltonian. I have a gadget that gives you any 5-body Hamiltonian. Okay, so there's a cluster spins, 5-body, 5. I can give you a gadget that defines now the new Hamiltonian on those 5 qubits, let's say they're qubits, plus ancilla qubits. I don't care much. And that new body, and there are only 2-body interactions between these guys. And I can show, this is the Hamiltonian on this guy, and I can show that the low energy theory of this Hamiltonian gives you this effective Hamiltonian. Now, so actually you can do that for any, K body, I can reduce to 2-body. But I'm not saying this is very efficient in the sense that I need additional ancilla and so on, additional degrees of freedom to do this operation. So with these, if the K is very high, you need a lot of ancilla. So it's not necessarily very pretty, but it's a procedure that works. So what we do is we say, well, we know that estimating your ground state energy for this model is hard. But this model has, as a low energy theory, this model. So we can actually show that finding the ground state energy here is also hard. Right? Because if we had the ground state energy here, it's actually having the ground state energy here. So unfortunately, this is really, let me see, I lost the notes here. This is the only trick that we have right now in QMA to reduce one problem to another. So like I said, we don't have good methods for reducing one problem to another. Okay, so there are questions now? Okay. I understand that it's a little hard to follow how this goes in detail, because I'm not giving you any of these perturbation gadgets, but I want to give you an idea. Okay, so let's talk now about 1D. I promised that I would talk about 1D classical spin systems. Okay, what's the efficient algorithm Why are 1D classical systems easy? Okay. So, so I have a spin system, which imagine something like this. This could be a single spin, but let's assume just that it's kind of a cluster of n spins. Right? Because maybe this one chain has a certain thickness. So it's like a block spin. So every one of these spins can take values -1 and 1. So we can represent this as a vector which has, n entries, n eigenspins. Okay, so let's say this is a chain. This is R plus 1. The whole chain has n links, right? So the whole Hamiltonian plus 1. Okay, so let's look at a part, because I'm going to describe to you what's called the dynamic programming technique. Does anybody know this? Dynamic programming? Okay, a few people are nodding. Okay, so the dynamic program, so I could define the Hamiltonian up to spin R as follows. Minus 1, h, I plus 1. So this is the Hamiltonian sort of up to here, right? And the idea is the following. So for a one-dimensional chain, a very simple thing is right. If I look at the Hamiltonian for this part of the chain, and including, say, this interaction, then the optimal value for the energy for this part of the chain only depends on the spin configuration here. Of course, that optimal value does not depend on what the spin is here. Right? It just, because there is no coupling between this spin and that spin. So I could determine the optimal value of the Hamiltonian here given a certain boundary condition. I can say, let me set this spin, let me run through all its possible values, or 2 to the n values. And given that boundary, I can do this optimization. And then I can store that value. Yeah? And then I can go on to the next, then I make this chain a little larger. Okay, so let me state this more formally, that the optimal value of the energy function for the chain up to pretty much I have enough time here. Oh, sorry, let me just erase this here. So H opt. So I set my R plus 1 spin to some value S, and I'm going to take, calculate this for different values of S. So this is the optimal value of the Hamiltonian, sort of until here, setting this spin to these values S. That this is clearly the minimum over S prime. So I'm relating this quantity to this quantity. How am I doing that? I can say, well, what is this optimum when this is set, if this spin is set to S? Well, it's equal to the optimum here when this spin is set to S prime, I'm going to minimize over S prime, and I have to add this interaction. Right? So that's what this expresses. It's the minimum over S prime, which is this spin, which is the values that this spin takes. And then I can use the optimal value of the spin up to R, given this S prime, and I add the new term. So how do your algorithm proceed? Because the idea is that, so you can calculate this, if you've stored this, and you do this little optimization, which is only over the spin S prime. Huh? So you store, let's say, this guy. For 2 to the n values S. You have to store the optimal configuration for the first 2 spins given this boundary, and I'm storing it for all values of this boundary. Because I'm not sure what value of the boundary is going to be the optimum there. I have to use that later. And then I compute this using this formula. I have to compute this for, let's see, for 2 to the n values of S. So I can put that into this formula to do this for 2 to the n times, and for every time I have to do this minimization. And when I do the minimization, I invoke these numbers. Yeah? So using H2 opt sigma 2x for all these variables. And then of course I store the next number. Etc. So I go along the chain like this. Okay, what is the efficiency of this algorithm? Well, it's clear. It takes order n steps. So this is something that just goes along the chain of length n. What do I have to do in every step? Well, I have to compute something for 2 to the n values. That's the dimension of this spin space. That's the number of states I have in there. And for those 2 to the n values, for each of those, I have to do a minimization over 2 to the n values of this S prime. Now, let's say I do this minimization brute force, so I just cycle through all the values that S prime can be, which is 2 to the m steps. And then for every one of those minimizations, I have to calculate this. Right? It's just a 2-body interaction. I set these values of the spin, so let me call that t, the time it takes to evaluate r plus 1 S prime. Yeah, it's just a single term. The algorithm is not going to follow a stand on this. This could be this could be of order n. The cost, of course, is this, in the sense that the algorithm is linear in n, but if my spins are large, if these spins take many values, meaning the chain is kind of, it's like a strip with a thickness which is pretty large, this is going to be costly. So it's an efficient algorithm in n, which is what, for a chain for which this is of constant, not growing in n dimension, but it may not always be efficient in practice. Now, one thing you can do, this is called dynamic programming, this idea of storing partial optimizations over, over a variety of boundary conditions and using them later, and just to do the next optimization. So dynamic programming can also be done on a tree. A tree, like, it's, instead of a chain, you have something like this. It's similar because, the thing is that if you come from here, the optimal here only depends on the spin configuration there at the boundary, not on something like that. So dynamic programming on a tree is also efficient, or on something which we call, well, there's a more computer science technical notation, or tree-like graph they have bounded tree with. So there are even more generalizations. This is not readable probably. Okay, so there are generalizations. So this is the reason that in a 1D classical system, there is never any issue of NP completeness. That's never required. So the obvious question now is to say, how can we generalize this to quantum systems? Right? Can we do the same thing for a quantum system? Well, yes and no. Let me first, and this was recently discussed by Schuch and Sirac and Aronov, Arat, and Irani. I give the references or just the dates. All these papers are available in the archive. Okay, so let's first do example. You say, well, maybe I have a quantum system, but let's assume something, maybe it simplifies the problem too much, but let's assume that the ground state is just a product state. So now I have a chain of d-dimensional spins, or d-dimensional quantum states. That's what is a basis from 0 to d minus 1. That any superposition of these states is possible. And I'm going to assume that ground states, so this is the ansatz. I have a ground state that the ground state is a product. It's just a product of states, one for every spin. Now, this of course this is sort of like the simplest generalization from classical, because I don't have any entanglement. And intuitively, you can also see that the same property that we have here, that if I have this ground state ansatz, and if I would look at the optimal value over this product states, right, this you have to, for spin, let's say up to spin r, that of course doesn't depend on what the state is at the other end of the chain, right? Because there's no entanglement. So you can do the same procedure as you do for the classical spin system. The only thing is, how many, here I have to calculate the optimal value for part of the chain, varying the boundary condition. Now, what should I choose as the boundary condition? What value should I let it be? Well, I could, if I'm sort of stupid, I could say, well, I'm just letting it be these states, 0 to d minus 1. These possible states. But that kind of assumes that the optimal value will be achieved when these states are, one of these basic states. And then it's kind of a classical problem. So we should take a larger set of states. Ideally, what we want is we take one of these spins. This is a d-dimensional spin, d-dimensional system, and we would take kind of a discrete approximation to the set of all states, right? And that's called a net, right? So you could say, if I have a d-dimensional spin system, how many states k do I need to approximate any state with a certain accuracy? Any state sigma with accuracy epsilon, yeah? So for example, this of course is a continuous number of states, but I want to discretize it such that I can approximate any state in that space, let's say psi, with an accuracy epsilon. So there's a discrete set of states such that for all psi, there exists an element of discrete set, let's call it this number I, such that this it's larger than 1 minus epsilon. And that would be an epsilon approximation. So how many states do I need for that? And so this is something that people have looked at in quantum information theory, and it goes like, can you see the order there? Let's see. So the number of, so this is called an alpha, epsilon net over the set of states. And this goes like a constant divided by epsilon to the power 2d. Well, the d is not important. So, what does it say? Kills exponential with this thing. So it's not so nice. Huh? Well, let's say maybe this, asking for a very high accuracy is a little bit overkill. Okay, now, one thing. So let's just fix this. Let's just say I fix the number of states that I'm going to look at for every space. Let's fix that to be k. Now, how does this dynamic programming algorithm then scale with that k? Well, in this case, I took this set of states that I look at to be 2 to the n, right? And it's just the square of that. So we expect that for product states, dynamic programming, well, okay, so the time will be something like n times k squared. Right? And k squared is the number, and there may be some factor like this, but k is the number of states that I allow as my boundary state. Right, but the problem is that for high accuracy, k needs to scale badly. And so again, it's not clear this is very practical. I don't actually know whether anybody's done this explicitly to see how good it is, or to take an epsilon net, because this is fairly new work. Now you can say, well, can we go beyond product states? What about those matrix product states? I have an ansatz, which is a matrix product state. Now, there's some entanglement, but perhaps I can show that also something like this holds, that the optimum over the optimum value of the energy, minimized over a matrix product state, only depends on something at the boundary. It turns out that you can prove that something at the boundary is like this matrix. The matrix product state is characterized by these matrices. Yeah? So you have a matrix A, I, R. So the optimal value of the Hamiltonian only depends on the matrix that you had at the boundary and something that we call rho R, which I think Frank referred to as something where rho R is something like A R minus 1, there's some, I actually don't recall exactly, but there is some additional information that you need to keep. But basically, I don't want to go into detail because it's quite an involved procedure to show this explicitly, but it again shows that minimizing over matrix product state, the optimal value for particle chain only depends on properties of this spin, which are not captured by that matrix of the matrix product state you have there, and some additional numbers, this is rho R. This is probably one of the reasons why DMRG works so well. Yeah? Now the authors of this paper, they say, well, okay, we make this. They devise a polynomial time algorithm to minimize over these matrix product states. So it's polynomial in n, but you have to look also at how it scales with this bond dimension. This bond dimension of the matrix product is constant, and how it also scales with the d of the d-dimensional system. So the problem is that I'm not sure I want to go into this. So again, like you saw here, if you want, so here you took for the product state, you took an approximation of the discrete set of states. Now you have to take an approximation of matrices, right? These matrices in matrix product state, it can be anything. But what this algorithm prescribes, you say, well, you discretize this set. And how many do you have to take? Well, again, this scales pretty badly in the accuracy. So I think it's somehow it's sort of a stupid method because you say, well, what I like to set these matrices to be is something that I get maybe from another optimization, right? Because otherwise I start with, well, I can describe a set of matrices and I get a lot of them and I have to calculate the optimal value for all of them, but they're probably most of them are completely irrelevant. So I'd like to, so the question is whether this algorithm that they described, which is polynomial n, can be made a little bit cleverer, maybe in combination with the DMRG methods. Now, one thing I'd like to note is that there is no hope. So this is why I want to show why these complexity theory results are important. You say, oh, well, maybe I can find an algorithm that for any 1D chain, I minimize over the matrix product state, and I get an algorithm. So this is the question, can I get an algorithm that scales like, this would be great, but polynomial in the bond dimension, so this is a constant, of course this is irrelevant, polynomial in n, preferably linear, and polynomial in some 1 over epsilon, and epsilon is the estimate for the ground state energy, right? So lambda h is the ground state energy, and I will get some approximate value, and I guarantee is this an epsilon. Can I get this? No. No. So why not? Well, again, it was shown by Schultz-Sirach for start in 2008 that there are classes of one-dimensional Hamiltonians with unique matrix product states. They showed that the bond dimension of the polygon. And that finding this matrix product state that minimizes the energy is as hard as factoring. Is as hard as factoring large numbers, which is in NP, which is not known to be complete. They have an extended result. So the point is here that so they constructed a Hamiltonian or a class of Hamiltonians for which they could prove that indeed, it had a unique matrix product state, ground state, with bond dimension bounded in this way. But if you would find this matrix product state that minimized the energy, let's say via this technique, then you would solve factoring, right? You would factor large integers. Now this seems like, well, how do they do this? And this is really where the power from this complexity theory comes from. Because what they did, they used this construction and they used this QMA results to prove a thing like that. And so they show that you cannot hope that there's an efficient algorithm like this, minimization over a matrix product state, that gives you, a strict bound on the energy and has this running time. Now, what I've talked about are all, this algorithm is rigorous in the sense that you look at, you say, okay, I want the bound on the energy estimate that I get that is at most epsilon. And then I look at the running time. The DMRG, of course, does never give you, well, it gives you heuristically, it gives you a bound. But it's not written that it gives you a priori promise that the difference between the real energy, the real minimum energy, and the one that you get is like a third or something. You don't get that. So that's the difference between heuristics and algorithms like this. Okay, are there any questions? Okay, then I'd like to raise the board. So I'm going to come to my last topic, which is what is easy. And so I talked a lot about hard problems and also about some algorithms like dynamic programming that are efficient, but maybe that's not necessarily practical in all cases. And like I said, nobody has done this paper about matrix, doing this matrix product state optimization by a dynamic program. Nobody has implemented this far as I know. I mean, I think to implement it the way they describe it with the error bounds looks pretty horrendous. So maybe there are cleverer ways that one can do. And although, I guess people are pretty convinced that DMRG is a very efficient method, so maybe there's nothing much to improve on. Just a little dry this. Okay, so now I'm going to talk about two-set, quantum two-set. Okay, so yeah. So the reason I want to present this is that it makes contact with things that you've heard in Frank's lecture about real space minimization. It's not quite that, but it's you can also view it as an approximate method for like more complicated problems. Okay, so we know that classical two-set, which is the problem where every clause, has two variables, blah, 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 is in V. So, and now quantum, I'm going to prove that quantum two-set is in P. And so quantum two-set is you're given these, your n qubits, you're given these projectors, and these projectors just work on two qubits at a time. And 2 qubits out of n. Actually, maybe I want to make paper's going to get me stuff. Yeah, one thing I want to mention before, I think a very important question. Okay, so before I go into this, so I want to draw a line. And on this part of the line, I say hard for quantum computers. So I want to put an open question to you. It's a very general question, but I think not much progress has been made on this. So I showed that there were problems that are hard for quantum computers. Like quantum 4-set, for example. Now I'm going to show you a problem which is easy for classical computers. Quantum 2-set. Now, the big question, so in this conference also, we focused on things we could do with classical computers. Now, that's important because we have classical computers. It's the only tool we have right now. But we would expect, or we'd hope for, that if we start from problems that are hard for quantum computers, and we simplify them, and we let go 4 to 3 or to 2. Or we look at local Hamiltonian problem but under some restrictions. We end up with problems where either they're classical feasible or they need a quantum computer to solve them. Right? So the question is, what is called BQP, sort of useful use of quantum computers. Surprisingly little problems have been shown to be solvable by quantum computers, whereas a classical algorithm has eluded us. Or you could say, well, some of the classical problems that we look at, for example, if you have PEPs, state, or they're using isometries. Frank was saying if you have unitary operations, it's much harder to minimize over. Can we use quantum computers to minimize over? It's a clever use of quantum computers, which of course we don't have yet, but we hope to have in the future, that improve on our classical methods for solving ground state and other problems about quantum spin systems. Okay, so that is a question I think is very important, but it's not that easy. And the reason that it's not that easy is that classically, because we have classical computer, you use heuristics. And you just say, well, we ran it and it worked well, so done deal. I don't have to prove that it's converging. On the quantum computer, if I come up with a heuristic, well, I'm going to face a large group of theoretical computer scientists who says, well, prove that it actually converges. Prove that it does well. They say, I don't have the quantum computer to give evidence that it works well. So I think there's been not a lot of development in heuristics for quantum computers for that reason. And that people focus on actually proving something which is a lot harder than, or it's just different. I mean, it's a different kind of problem than coming up with heuristic strategies.
So,
Okay. Yeah.
so which problems have been shown to be more efficient in quantum computing?
On the quantum computer. Well,
Apart from the fact that
no, so there is well, there's Grover's problem, which is a searching, which is an efficient one. And there are lots of problems that use tricks that you use also in factoring large number, but they're number theoretic problems, so they're rather obscure. One thing, there are also problems that are BQP complete. And for example, estimating the partition function of a classical system with a certain error bound is typically BQP complete. Something about knot invariance. They're kind of esoteric problems that you don't think a classical computer could do it, but you're also not extremely interested in it necessarily. It doesn't attract a huge audience. And the only heuristic thing, which I think is quite interesting, is also a paper by Frank Verstraete and co-workers about a Monte Carlo sampling algorithm that runs on a quantum computer. So the idea is that for problems, Hamiltonians have a sign problem. You say, I want to do a Monte Carlo algorithm that gets me to the thermal state or the ground state. But I have a sign problem. So how would I do this on a quantum computer? And that is a heuristic, and I think it's if we have a quantum computer, that's going to be very useful. Because all these problems that have a sign problem, you just do that on a quantum computer. There's no reason to do this classically. But of course, this is future, dreams about future things. Okay, two set. I have to be a little quick now. Okay. So it's a sketch of the algorithm. I have a bunch of projectors acting on 2 qubits. And so I'm going to divide this. So I'm going to sketch how this works. And I have to, okay, what's the problem? I have to decide whether there is a state that is annihilated by all these projectors. Okay, so the idea is I'm going to give you a polynomial algorithm. I'm going to sketch you that there is a polynomial algorithm that decides this. Now, there was an improvement on this result. And I think also that shows you the power of this quantum information language. That shows that if there is a satisfying assignment, I call this SA, so there is a state that is annihilated by all these projectors, then that state is a product of single and 2 qubit states. What does it say? It says that the problem is in some sense a bit trivial. If there is a state that is annihilated by these projectors, then that state barely has any entanglement. Because what it is, it's a product of single qubit states and some product, 2 qubit states. This is results that I mentioned, I think by Chen et al. But who would have known? I mean, this is easy to prove. It doesn't look easy to me to prove that this is true. Okay, so how do we go about this? Let me see how far we get. Case 1. Let's assume that all projectors have rank 1. What is the rank? It's just a projector that has eigenvalues 1 and 0. Rank 1 means that it has one eigenvalue that's 1. The rest is 0.
Question?
Yeah.
If you relax, make it instead of qubits, you have like some kind of more states. Is it still?
No. That is then it becomes harder, and it's very interesting.
So it should be really special.
Yeah, and I think it's a very good problem to think about, like quantum 2-set on cube tricks. See, the thing is that if I do quantum 2-set on 10-dimensional systems, I could look at that as doing like quantum 4-set on qubits, right? Because I could look at quantum 4-set, which is hard, I say, well, I'm going to cluster these qubits, I take two qubits together, call it a four-dimensional system, and then I reduce it to a two-set problem, but it's now on higher dimensional systems. Yeah? But there is a gap between what's proved to be hard and what is easy. So I think the easiest step up is to do two-set on cube threads, and maybe with a special, I was thinking maybe if you have an SU2 symmetric Hamiltonian, maybe with a special constraint, because there's something that doesn't work for those cube threads in this algorithm. Okay, so this is an algorithm by Sergei Bravyi. It's on the archive. He actually never published it, but it's often cited now. Okay, so case fun is if all projectors have rank 1, then the problem is in special form, and we'll deal with that later. So what I'm going to describe, time permitting, is that when there are projectors that have rank larger than 1, so I'm going to check for all the projectors, I'm going to check their rank. Okay, so now that I have cases, okay, so first case, trivial case, rank of a projector is, remember these projectors act on 2 qubits, so the rank is maximally 4, right? So if it is 4, then of course there is no state that annihilates this, right? So we can't have that, right? The question is whether we can have this, right? Because all states are, it's just the identity operator on those qubits. So we conclude immediately there's no, the answer is no, there's no satisfying assignment. So now we can go to the next case, rank pi is 3. Now what is rank pi 3? I can write that pi. I'm going to switch notation. Let's say pi, can you see this? Pi acts on qubits A, B. The rank is 3. I can write it as the identity on A, B. minus a certain state. Yeah, so basically, if the rank of pi is 3, the null space is one-dimensional. There's only one state, namely that state, that is allowed. So this is simple, because it means that in order for there to be a satisfying assignment, I have to put qubits A and B in this state. So I'm sort of done with these 2 qubits. I put them in that state. Yeah, so the satisfying assignment I know, well, I'm going to write this on us. So this is the rank. More state, no, here. Rank pi is 3, then I know that if there is a satisfying assignment, it has to be of this form. This is qubit A and B, and then, something else. Right? We don't know yet. You can also say, well, there maybe were other constraints that act on qubit A and B, and I have to process these constraints. Yeah? So, for example, there was a projector PAD that I can now, Sergei shows how to process this. I have to replace this by a 1 qubit constraint on D. Huh? Maybe if this constraint, maybe it's true that having this state in this form and having that constraint immediately shows that I don't have a satisfying assignment. If it doesn't show that, I end up with potentially with some constraint on system D. And then if I have other guys, so I have other constraints, C, D, I just leave them alone, right? Because they don't have to process this constraint, and the others, they act on other qubits. So what happens here is that I have processed this constraint, and I've reduced, I had n qubits, but now I'm left with a problem on n minus 2 qubits. Right? Left alone. And we go from n to n minus 2. And maybe we decide it says. Okay, so 15. Okay, so now the next question. That's where it gets interesting. Let's say the rank pi is 2. So what it means is that there's a two-dimensional space is still allowed. So now, we kind of want to do randomization. You say, okay, let's say these are these two qubits. We want to merge, we want to process constraint, so we want to merge these qubits in a single qubit that represents that two-dimensional allowed subspace. Now how do we do that? That's called an isometry, right? So if I have, so in general, if I could do, let's say, this is, say, let's say, see, I start with two qubits, right? And they are in, you know, this is, let's say I take a two-dimensional subspace, and there's always a unitary, or this is, you know, U dagger this way, that maps that onto, you know, a single qubit space, right? And so that's, you could say this is a map, this going this way is a map from one qubit to two qubits. So this is what we call an isometry. And we have, this is the identity, so, but this is the projector onto allowed subspace. Allowed meaning those, if I'm in that state, this projector annihilates it. And so actually you can write, let's say these are qubits A and B, you can write pi AB as something which is 1 minus this V minus V prime. Right? So of course 1 minus V V prime on V V prime is 0. And this is vector. Okay, so what we do is we merge. So for every constraint where I have this rank 2, I'm doing kind of a renormalization step. Right? I could say, well, originally I had the candidate state, but now I know it has to lie in these subspaces. So I'm doing, let's say, this is like doing this upside down. This is gate U. So I put this as a gate where I start with 0, I do U, and then I have this 2 qubit space. And these U's are given by this projector. And let's say there's another constraint here. It's like this. And I do that for all these rank 2 constraints. And the good thing about these rank 2 constraints is that what I've left is still a qubit. It's not a qubit, it's not a higher dimensional thing. So I could do this again potentially. So I also have to process. Okay, so when I do this, I have to process other constraints, right? There could be a constraint pi AG, which acts on A and another thing. Right? So I have to take that isometry and push it through this constraint, because I've represented my possible satisfying assignment. I represent it differently. So this is this isometry. I define, and this operator now acts on this qubit C. So there's A, B, and that's merged into qubit C. So now I have a constraint that acts on C and that other qubit G. And this needs to be a projector, but you can just say, well, this has to annihilate the purported satisfying assignment. So I take the projector onto its null space, and I go on. You can show that the rank of this guy is diminished. So what you do with this procedure, so okay, what do we do in case 2? If this rank is this high, no satisfying assignment. If this rank is 3, you split off part of the space and you reduce the number of qubits that you're working with. If the rank is 2, you do an isometry and you process the other constraint and reduce their rank. So if you keep on doing this, you will end up with rank 1 constraints. Is that clear? All the steps in this procedure reduce the number of qubits and also reduce or keep the rank of these constraints the same. Now you could say, well, okay, so then we're in case 1. All projectors have rank Okay, so I'm gonna say one more thing. What's next? Can we keep on doing this? Rank pi is 1. And so if I follow, if the rank pi is 1, then there's a 3-dimensional subspace which is allowed. So I could still do this isometry, but then this would be a 3-dimensional space. Yeah? And that's where the trouble gets started, because, and this is exactly what I think Frank was mentioning early. If you keep on only doing this entanglement randomization, your qubits will start getting bigger and bigger. So this would be, say, also 3-dimensional. And let's say I have a constraint here. And now this is 9-dimensional. So if the rank is like, if that constraint is 3, then I do the isometry again, then I get a 6-dimensional space. And I keep on growing. So that's not going to work. So what I need to do, there's another trick, which is combining constraints. So I just break the lemma. And then I'll just stop. And this is particular to qubits and rank 1 constraints. So what is a rank 1 constraint? Well, a rank 1 constraint is just something like this. It's just the state, right? This state, the satisfying assignment has to be orthogonal to this state. Now, let's assume that I have some state which satisfies pi AB 0, and some other thing, pi, this is also 0. And these are both rank 1 constraint. Then Bravia shows how to produce another constraint, which is pi AC psi is 0. So he says, if these has to be true, then this also has to be true. And what you do is that, okay, so in case 1, you only have one rank 1 constraints. Now you look at all triples of qubits, A, B, C. How many are there? They're at most order n to the 3rd. And you make sure they're consistent according to this. Now, if for some reason you end up, let's say you already had some constraints here, and you keep on adding stuff so that you don't get a satisfying assignment, you say no satisfying assignment. But if you have a system of rank 1 constraints that all mutually consistent and checked in this form, then he proves that there is a satisfying assignment, and it's a product of single qubit states. Okay? So the whole procedure is, first, deal with the higher rank cases, reduce them by using isometries, or decide no to satisfying assignment. Then, once you're once you only have these low rank constraint, rank 1, you combine the constraint, and then you can show there is a satisfying assignment. That's roughly it. Okay, so the question is, can you make this a good approximation method for higher dimensional systems? Right? This is a way of singling out and moving into the satisfying assignment if it exists. So for example, these projectors, you could say, well, I'm taking the projector onto the low-lying eigenvalues. And not the lowest only, but I leave a little bit of error because I don't need a satisfying assignment because it doesn't make it exist. I need to find an energy state that has low energy. Okay, sorry that I'm going over, but any questions? People want coffee? Okay.